Okay, this video is dealing with thin lenses. And when we study thin lenses, they are very similar to the curved mirrors, which was the previous lesson or video. But along with reflection that was on the mirrors, lenses involve refraction. So there are two types of lenses. One of that are known as the convex lenses, and the other one that is known as the concave lenses. Convex lenses looks like this. Okay, so when we have a lens that has the two sides curved in this way, then those are known as the convex lenses. And when we have a lens that it looks like this, then we are dealing with those that are known as the concave lenses. So, okay, so this is for the configuration, just so you know. The convex lenses, those types here, are able to collect all of the reflected rays into one point. And a picture of it will be something like, I'll just bring a picture here. A convex lens will collect all the reflected rays at one point that is known as the focal point. So this line here is the principal axis. This is the center of the lenses, and the distance from the axis of symmetry of the lenses to the focal point is known as the focal length. As you see here, all of the reflected rays in the convex lens are diverging. Okay, so this is why very often those are called divergent lenses or convergent lenses, versus when we have a concave lens. As you see here, the rays, the reflected rays, are kind of open up, okay, and they are all passing through that is known as the focal point, and the distance from the symmetry of the lenses to the focal point again is known as the focal length. The equation that is used to deal even with lenses is the same as the equation that we have used on mirrors. So it is 1 over f, where f is the focal length, is equal to 1 over do plus 1 over di, where do is the distance of the object and di is the distance of the image. And magnification is hi over ho, where h is the height and I represent the image, O represent the object, or negative di over do. And they are the same as we had on the previous equation, where di is the distance of the image and do is the distance of the object. Focal length, if focal length is, so f as focal length, if it is real, then we have a plus, like we use the plus convention, and if it is a virtual, as minus. Distance of the object, do, is always positive. Okay, the same thing as we did even for the mirrors. Distance of the image, it is, if the image is real, then it's positive, and if the image is virtual, is negative. Height of the object is always positive, HO, and the height of the image is negative. Height of the image, if it is real, is negative, and if it is virtual, is positive. So magnification, when it is a real and inverted, will be negative, and if it is a virtual and upright, will be positive. While the equations for curved mirror and thin lenses are the same, it is important to note that the real image formed from the front of a mirror and the real image from the behind a lens. This is due to the fact that mirrors reflect light back, while lenses refract light through the other side of the lenses. Let's see now some cases in which the image is created as a result of the rules that we apply for the ray diagram. So for the rules that we apply for the ray diagram is, if the incident ray is parallel to the principal axis, then it passes through the lens. In passing through the lens, will be going through the focal point. And if it is the incident ray is passing through the focal point, then in the refracted one will be parallel to the principal axis. The ray passing through the center of the lens, it goes straight through. So those are the three rules so that we will apply to draw the image formed as a result of the ray diagram. So the first one was saying that when we have a focal point here, the object is here parallel to the principal axis. It is passing, so this is the incident ray, it is passing through the focal point. This is the reflected ray. And it doesn't matter what kind of lenses do you have. You may have a concave or convex lens. Still is the same thing. So if this is the principal axis and you have an object that is here, this is the object, then parallel to the principal axis, the incident ray, let's say that here is the focal point, and then we will have the incident ray, the reflected ray as passing through the focal point. The second law that I just mentioned is when it is passing through the focal point, then it is reflected parallel to the principal axis. So when we have lenses, here is the principal axis, not that much as a principal axis, then here is the focal point, then you have incident ray, it is reflected parallel to the principal axis, and it doesn't matter, as I said, what type of lenses you are dealing with, they both will be the same thing, the same principle. So you have the object here, and then you have the focal. And it is parallel to, so this is the incident ray, and it is parallel to the principal axis. And when the third rule is when the incident ray is passing through the center of the lenses, which is the point that intersect the principal axis with the symmetry of the lenses. So here is the object. This is the incident ray, and then the reflected ray will be this one here. While when we have the other lenses and the object is somewhere in here, then the center of the lens is here. That means that we'll have this as the incident and this as the reflected. So it just goes straight through the lenses. Now let's bring some pictures in which we are explaining what is the image created when we have different positions of the object relative to the lens. So by having those nice pictures, you will see better, and my ugly drawing will not be that misleading. So let's see the first option when the object is beyond the center of the lenses. So if this is the focal point, then this one double, because still the same thing is that radius of the center of the lens is double the focal length. So this is the center of the lenses. So now the object is beyond the center. Now the first rule is saying that when the ray or the incident ray is parallel to the principal axis, then the reflected ray, so this is the incident ray and this is the reflected ray, it's passing through the focal point. And when it is passing through the focal point, then it is reflected parallel to the principal axis. You may not apply the third rule, because what you will be able to see is the intersection of the two reflected rays, and this will create the image. So if this is the object, if this is the object, then this is the image. As you see, the image on this case is it is inverted. It is real because when you draw the ray diagram, then the point of intersection is not an extension of, but it is just a direct intersection of the two reflected ray. However, it is inverted because it's on the opposite orientation of the object, and it looks smaller than what the object is. Let's see now a case where the object is right at the center. So in this case, so we will apply the two rules, because the third one is kind of like a just in case if you cannot figure out what is the image created applying the first two rules. For what you are doing on Physics 30, it's good enough to use the two rules. So what do you see in this case is that the reflected ray parallel to, or incident ray parallel to the principal axis is passing through the focal point. And from the center of the lenses, it is going toward the, it is going through at the same line. So this is the incident ray and this is the reflected ray. The 2 point of intersection of those two lines is visible, so you don't have to extend those lines further, therefore the object is real. It is inverted because it's in the opposite orientation of the object. And on this case, the size of the object is the same as the size of the image, which tells us that magnification is equal to 1, just on this case. A third case is when the object is between the center and the focal point. So if we apply two of the rules, then we will find that the image created is real. Why is it real? Because the reflected rays, those both are reflected rays, have an intersection, so you don't have to further connect them, but the intersection is to extend them. The intersection is real, but it is inverted. It is on the opposite orientation of the object, and it is larger than the object itself. Next case is when the object is right at the focal point. And as you see here, those two reflected rays are parallel to each other. So therefore, it doesn't matter how much you are extending them, they will not intersect because two parallel lines will go infinitely, not touching each other. So this tells us that there is no image that is formed. And actually math proves this fact. So the distance of the object is what is equal to the focal point. So the distance of the image will be non-existing. And the last one is when we have an object that is between the focal point and the lenses. So as you see here, the image that is formed is as a result of the extension of the reflected rays, which makes the object a virtual object. Okay, and it has the same orientation as the object. They both are going up, and it is larger than the object. So those are the cases that you kind of have to keep in mind, or the rules that you have to apply when you are constructing the ray diagram to figure out what is the image formed. The same rules will be applied even when we have a diverging lenses. So in this case, we have the object that is between the focal length and the center, and then the incident ray parallel to the principal axis will be reflected passing through the focal point. The incident ray passing through the focal point, so this one here, it is reflected parallel to the principal axis of the line of that disc, that the intersection is the image formed. So in this case, what we will see will be a virtual image, and it is erect, has the same orientation as the object, and it is smaller, is diminished. Okay. Those are the rules so that you have to apply. Usually for physics 30, as I said, it's very easy when we have, most of the cases we have to apply only the 2 or 3 rules, but just in case the third rule is like a backup for you to figure out which one is, like what is the image formed. And always when the reflected rays are having an intersection that is the reflected ray, not the extension of the reflected ray, then the image is a real one. Otherwise, it is a virtual one. Let's move now to some questions that are like word problems. So let's suppose that we have an object that has a certain, it is 4 centimeters tall, and it is placed 50 centimeter away from a convex lens that has a focal length of 20 centimeters. The same deal even with this. We have that case where if the units are the same, centimeters all the way through the question, then we don't have to bother converting them into meters, which is the international system unit for distance. However, on this case, what do we have is the height of the object is 4.0 centimeters. The distance of the object is equal to 50 centimeters, while the focal length is equal to positive 20 centimeters. Why am I saying it is positive? Because what we are doing is we are dealing with convex or converging lenses. We do know that we are dealing with convex or converging lenses because the question is telling us. Now, 1 over f is equal to 1 over do plus 1 over di. And from here, we figure out that 1 over di is equal to 1 over f minus 1 over do. In terms of the ray diagram, we are on the case where the object is beyond the center, because double the focal length will be 40, and now the object is 50 centimeters, so we'll be on the first case here. Okay, so this is what you have to expect in terms of the ray diagram. So now 1 over di is equal to 1 over 20 minus 1 over 50. And this will be 0.030, 1 over centimeters, which means that di is positive, and it is positive number, 33.3 centimeters. And if we take a look at what is the height of the image, then we'll use the magnification. Hi over ho is equal to negative di over do. And then from here, we can find that the height of the image is negative 2.67 centimeters. And that is telling us that since the distance of the object is positive, that means that it is image is real because it is positive. And it is inverted because we see the height of the object, but it is inverted. So since the height of the image is negative, then the image is inverted. And it is smaller because the ratio between the height of the image is smaller than the height of the object. Okay. Let's take a look on another question. If we have, let's say, a 5 centimeter tall object that it is placed into diverging lens now, and that has a focal length of 40, and it is placed 60 centimeters away from the lenses. Now, what do you have here? If the focal length is 40, then double the focal length is 80, and the object is between the center and the focal length. And you are dealing with diverging lenses, which means that you have something like this. in terms of the ray diagram. The focal length here, the center is here, the object is somewhere in here. Okay, so if you want to visually see, then you will see, you'll have to draw something like this. However, math will tell us what it is. So we have the height of the object as 5.0 centimeters. We have the distance of the object as 60 centimeters. Those always are positive. We don't discuss the sign of the height of the object and the distance of the object. However, the focal point that is given as 40 centimeters, since you are dealing with a diverging lens, is negative. So now, starting with the equation of the mirrors, dI will be 1 over f minus 1 over dO, which means that will be 1 over negative 40 minus, that is from the formula, 1 over 60 centimeters. And when you do the math, the dI will be negative 24 centimeters. And we know now what the negative means that we are dealing with a virtual image. Let's take a look now to what is the height of the image, and if it is erect or if it is like upright. So on this same as the previous one, HI over HO is a negative DI over DO. And from here we find that the height of the image is DI times HO divided by DO. So cross multiply two that you know with the negative sign and divide by what is left. And this will be equals to positive 2 centimeters. The fact that it is positive tells us that the object is erect. However, since the height of the object is greater than the height of the object is greater than the height of the image, then we can say that the image is diminished. I hope that this makes sense. Let's bring now another question. So in an experiment, what we have is what we have optical devices. When the object is placed 20 centimeters from the optical device, the erect image of the object is formed in the opposite side of the optical device. The image is 1/4 size of the object. What kind of optical device is this, and what is the focal length of the device? Okay, so now we see that the object is the image is erect. It's because it is saying here the image is erect, meaning that it is smaller. Okay, so and it is on the opposite side of the object. So now we have the case when we have a virtual image that is on the other side of the object. The only way that this can happen is with convex or diverging mirrors. Okay, so however, let's let's see and talk, do the math and see this. So what we have is that the distance of the image, the formula is like this: magnification is equal to negative DI over DO, which means that we can say that since DI is 1/4 of DO, because it's saying here that it is 1/4 of the DO. Where is it? 1/4. Okay, 1/4 of the size. Then we can figure out that DI we can figure out that DI is negative 20 centimeters over 4, or negative 5 centimeters. Okay, so since DI is negative, that means that you are dealing with an erect image. Now let's deal with the formula. So we'll have 1 over F is equal to 1 over DI plus 1 over DO. And then from here we can say that 1 over F is equal to 1 over negative 5 plus 1 over 20. And we find that the focal length is negative 6.67 centimeters, which proves that you are dealing with convex mirrors. Okay. This concludes the lenses. If you have any questions, then we will discuss them in class. And after this, we'll move to interference and diffraction and polarization. So hang on.